Imagine you have a secret diary and you toss it into a roaring campfire. You watch as the paper burns away, leaving behind nothing but drifting ash and rising smoke. In our everyday lives, that diary is gone. You can't read a cloud of smoke, so we assume the thoughts written on those pages have been erased from existence. But in physics, information isn't about the words we read. It refers to the specific, unique way the tiny particles making up the paper and ink are arranged. This leads to a rule that sits at the very foundation of the universe, the law of conservation of information. It states that while you can scramble or hide information, you can never truly delete it. If you had a powerful enough computer, you could track every single molecule of smoke and every speck of ash to perfectly rebuild the original diary. To the universe, everything is reversible. Objects might get jumbled up, but their history is always preserved somewhere in the mess. But what happens if we move this scenario away from the campfire and into the depths of space? What if we throw that same diary into a black hole? Albert Einstein's rules for gravity tell us that a black hole is the ultimate one-way street. Once the diary crosses the event horizon, the pull of gravity is so intense that not even light can get back out. At first, this isn't a problem for our rule. The diary is trapped and we can't see it, but its information is still there, safely locked away inside the black hole's interior. As long as the black hole exists, the information is preserved. It's in a vault that we can't open, but it hasn't been destroyed. In 1974, Stephen Hawking looked at the edge of that vault and realized it had a leak. He discovered that black holes aren't actually permanent. To understand why, we have to look at the vacuum of space. It's never actually empty. Instead, pairs of tiny particles are constantly popping into existence, colliding with each other and vanishing in a fraction of a second. But at the very edge of a black hole, gravity can pull the pair apart before they collide. One particle falls into the dark, and the other is ejected out into the universe. Because those escaping particles carry away energy, the black hole loses mass. It begins to emit a faint glow called Hawking radiation, and as it does, it slowly shrinks. This means black holes aren't forever. Given enough time, they will eventually evaporate away entirely. Trillions of years into the future, as the black hole gets smaller and smaller, its evaporation speeds up. In its final moments, the black hole disappears in a violent flash of energy, leaving behind nothing but empty space. When we look at all the radiation left behind, we find that it is completely random. It's just featureless heat that tells us how heavy the black hole used to be, and nothing more. This radiation is like a pile of blank paper. Whether you threw in a diary, or a desktop computer, or even a star, the energy coming out looks exactly the same. It contains no traces of the specific objects that fell in. This is the paradox. If the black hole is gone and the radiation is empty, the information has been deleted. If that's true, the rules that govern all of modern physics have failed. To solve this, scientists are stuck with a trilemma. 3 choices where every single path breaks a fundamental law of nature. The first path is to accept that information is truly destroyed. This would mean our most basic rules about how particles behave are simply wrong. The second path suggests the black hole leaves behind a remnant, a microscopic speck that somehow holds an infinite amount of data, even though it has almost no size or mass. The third path, information leaks out in the radiation, preserving Quantum rules. But escaping breaks particle connections, creating a massive energy firewall. Anything falling in is instantly incinerated at the horizon, breaking Einstein's rules of gravity. Scientists are trapped. Saving the rules of the very small requires breaking the rules of the very large, and vice versa. Even though it seems like a dead end, physicists see this paradox as a map. It points exactly to where our understanding of the universe is incomplete. The goal is to find a theory of quantum gravity, a single set of rules that works for both giant galaxies and tiny atoms. This search has already led to the holographic principle, the idea that our entire 3-dimensional world might actually be a projection of data stored on a flat 2-dimensional surface. Solving the riddle of the cosmic shredder will finally show us how the smooth geometry of space and the chaotic lives of particles fit together into one single unified picture.